This is our supplementary lecture for Thursday for the class that I will not be able to teach on Thursday since I will be out of town. As a review, last lecture we talked about the ideal MOS transistor theory. We talked specifically about how applying a threshold voltage at the gate creates an inversion region, and that inversion region allows the channel to be created. And that what happens when the arrangement of the voltages on gate, source, and drain creates saturation. That causes a pinch off, and that also has to do with parasitic capacitance. What happens when capacitances that aren't just between the gate and the body, such as source and body, drain and body, source and gate, drain and gate, those types of capacitances are parasitic and impact the actual transistor operation. We also learned that saturation can often be created by these ideas of mobility degradation, and saturation can be caused, it has a profound impact on the operation of current from the drain to the source, particularly channel length modulation, how the length of the channel impacts the capacitance. We proved that in cutoff linear saturation, we proved this table where we indicated that half of gate source and gate drain is indicated in linear mode of the output capacitance. We know CO, which is equal to EOX TOX times WL, or EO times KOX, which is the permittivity of free space times the multiple of the permittivity of free space by silicon, which is 3.9. And we know that the thickness of the oxide, is given in a problem, would allow you to determine the actual gate capacitance. We also learned about the effective mobility of electrons in holes using these equations. They'll be provided on an exam sheet. We also learned about velocity saturation and how increased scattering of these electrons actually start colliding with one another, and that we know that the electric field is related to the drain source voltage divided by the length. That means this is an issue that as we get smaller and smaller transistors, we're increasing the electric field, which possibly corrects these higher carrier velocity electrons as they start colliding, and then you get lower drain source voltage than you would expect. So the first example question of this lecture is we're going to combine this idea of electron and hole mobility and be able to calculate this critical voltage. The question states, consider an ideal NMOS transistor, so that's where we're going to start here, in a 0.6 micron process with minimum draw channel length of 50 nanometers. The threshold voltage is 0.3 volts and the gate source voltage is 0.1. Compute the effective mobilities for NMOS and PMOS transistors when they are fully on. Next, determine the critical voltage for both NMOS and PMOS transistors. So we start with our given equation, 540 centimeters over voltage per second, plus divided by 1 plus the quantity voltage gate source plus threshold voltage of 0.54 volts over nanometers times the thickness of the oxide. Now, solve this. We know that we are given in our equation sheet that's 1.05 nanometers, or 10.5 times 10 to the negative 8 meters is the general thickness of the oxide. We know that 0.54 is given in the problem. We know 1 from VGS and 0.3 is given from our threshold voltage. Substituting that in, we get 9.72 centimeters squared over volts. The effective mobility of holes is given by this equation as well. 1.85 centimeters squared over volts per second divided by the quantity 1 plus the absolute value of the gate source voltage plus 1.5 times the threshold voltage, 0.338 volts over nanometers times the thickness of the oxide. Again, we put it in nanometers because the nanometers cancel out, so it's 0.388 times 1.05 nanometers. And then here we have 1.0 plus 1.5 times 0.3. 1.0, of course, being our gate source voltage, and our threshold voltage is 0.3. This comes out to 36.37 centimeters squared over volts. Then we take this mobility and we use it to calculate our actual critical voltage. So we know that critical voltage is equal to the electric field, the critical electric field times the length of the channel. We also know that the velocity saturation of electrons divided by the effective mobility of the electrons times 2 is equal to the critical electric field. We defined 10 to the 7 as our velocity saturation of electrons that is given on your equation sheet for your exam. And we take this 95.72, we substitute here, multiply by 2. We then multiply the length, we have 50 nanometers. To make the units work, we convert that to 5 times 10 to the negative 6 centimeters. So we know that the centimeters here cancel out. Velocity centimeters per second, so it's going to cancel out completely. 2 times 10 to the 7 divided by 95.75 times 5 times 10 to the negative 6 centimeters is 1.04 volts. For the critical voltage for holes, we do the same thing. We have the critical electric field times the length of the channel, 2 VSAT P times the effective mobility P. We've defined it already as 8 times 10 to the 6 times 2 divided by 36.37, which we got from here, times 5 times 10 to the negative 6, which is our 50 nanometers that we found out earlier, and this is equal to 2.22 volts. So that is example question 2.3. Next, we're going to define channel length modulation. We formally define it as a reduction in the channel length by an increase of the depletion layer width at the drain as drain voltage is decreased. So here we go. We have our depletion region around the drain, and this is caused by higher drain source voltages, which also shortens the channel. Because remember here we have P and NMOS, right? So remember at the beginning of the semester we talked about diodes, and you put diodes together and effectively forms a forward and reverse bias operation where it's only current can only flow in one direction. When it's reverse bias, it begins to form a depletion region. Well, that is what's happening here in channel length modulation. The reverse bias PN junctions form the depletion region, and the width of the depletion region has this reverse bias, and it shortens the effective length of the channel. Now, the shorter length of the channel is going to end up providing more current because IDS increases with VDS. So we have our higher drain source voltage, and that causes the current to increase as well. And so the effect of the channel length modulation, modify our equation a little bit here. We have beta over 2 of gate source voltage minus VT squared. So remember, beta is going to be COXWL. So that's the oxide capacitance per unit area times the width times length over 2 VGS minus VT squared times 1 plus channel length modulation coefficient times the drain source voltage. So here we're talking about it's not a feature size, and usually you figure out what it is based on what you're expecting from your IV characteristics as opposed to what actually ends up happening. Your drain-induced barrier lowering, TGO 2.21, we define as the effect of the drain voltage on the output conductance and measured threshold voltage. And this occurs in devices where only the gate length is reduced without properly scaling in other dimensions. So this is Dibble. You'll often see this as DIBL, as you see here. And this is a very good description right here. So you have where you're expecting the drain voltage on the output conductance, your gate source, but now we have drain source current. We are expecting this to be higher, and it decreases because we haven't properly accounted for all of the proper scaling from all of the other length, width, voltage at the source, voltage at the gate, etc. So this is one of the benefits of this. You have to account for lower voltages in smaller feature sizes. So you have your normal threshold times your Dibble coefficient times the expected drain source difference, and that becomes your effective threshold voltage. So now what we're going to do is we're actually going to go into describing how Dibble, this is example 2.4, explain drain-induced barrier loading, Dibble, using an NMOS device cross-sectional diagram. Why is it a concern today, and what can be done to reduce its effect? Show this using a circuit diagram. So we have our cross-sectional diagram. We have our NMOS transistor. We have our source and our drain. And we have our P well. And we have our gate. So Dibble is the threshold voltage lowering due to a high value of VDS. So this value here, the voltage difference between the drain and the source, is much higher. When the large drain voltage is applied, part of that drain depletion region extends the channel, which acts to assist in the inversion process. So what's happening is you have a very, very high, excessively high drain source voltage, and it lowers the lowers the amount that you need to apply for threshold voltage in order to create the to lower the barrier. So that's why when you've lowered the barrier, you've now increased drain source voltage. So tie this back up here. The drain source voltage increases because the barrier has been lowered, the amount that you actually need in order to actually create the inversion region, create the channel. So the problem is that, as we learned earlier, dynamic power consumption and static power consumption are both directly proportional. Static power consumption is dynamic power consumption is CL, the load capacitance, times VDD squared. So if you're increasing this drain source voltage by a factor of 2, you're increasing the power consumption by a factor of 4. So even though you're reducing the barrier, what you end up doing is you're consuming a lot more power. So you have to worry about that aspect of it as well. So we're going to go into a lot of detail of something known as the body effect. I've kind of alluded to this a little earlier in the course. We have our body here. And to this point, we have assumed that the voltage on the body is at ground. This is not always the case. There are cases of forward body biasing where you have a positive voltage, or negative body biasing where you have to worry about where you're actually lowering the voltage even further. Now that you can actually kind of extrapolate how that's going to occur. When you're creating this difference at the well here, you're affecting the ability to actually create the inversion region versus being accurate. So if you lower the body, that creates more capacitance here. So you actually may have runs faster, but you have to worry about accuracy. If you put a positive voltage on the body, what ends up happening is that it's a little harder. It's harder to create the charge, but once you do, it's actually much more accurate and consumes less power. So we're going to talk about this concept called the body effect, which we are going to formally define as the impact of source body voltage, the surface potential at the threshold voltage, the doping level, and the intrinsic carrier concentration on the final threshold voltage. So we have this initial threshold voltage, which we believe will be, and then we have our intrinsic carrier concentrations. We have to worry about the doping level, which we'll define as Na, and we symbolize the body effect coefficient. So down here in TGO 23, we'll talk about the definitions there. We know Q is the constant charge for electron. ESI is the permittivity of silicon, which before now we were talking about SiO2, which is 3.9. Here we're going to find as 11.7 times the permittivity of free space and our initial threshold voltage. Here we go. The first equation is what's known as the body effect coefficient. This relates the permittivity of free space, the permittivity of silicon, the intrinsic carrier concentration, the charge, and the capacitance of the oxide. These are all important because you need to know how much have we doped the silicon that we're comparing in the body. We have to know the permittivity of the silicon because we have to worry about how fast the holes and electrons can travel through the space, particularly in a channel. We need to know the charge since we're calculating all the charge based on the fact that we're using the gate and transistor as a plate. And we need to consider the capacitance of the oxide itself because the capacitance has impact on both current and voltage. Next, we're going to calculate the surface potential. So now we have our threshold voltage. Sorry, we have our velocity times the natural log of our doping concentration times the intrinsic carrier concentration. So when we deal with this kind of stuff, we have our doping levels and we have our fundamental intrinsic carrier concentration at room temperature. So that's why I've included, when you see this example problem we're going to work on here in a minute, at room temperature, that means it's perfectly valid to use this intrinsic carrier concentration. Finally, using these two values, you can actually calculate the new threshold voltage based on your initial threshold voltage, plus the body effect times the quantity, square root of the surface potential, plus the source base voltage, minus the square root of the surface potential. So we're going to define the thermal voltage at 0.26. That's the thermal voltage, not the threshold voltage. I misspoke. Thermal voltage will be used to calculate the surface potential. And we define that by using Boltzmann's constant times the temperature divided by the charge of an electron, which has been calculated for you at 0.026 volts or 26 millivolts. For example question, we are given an NMOS transistor at room temperature in a 65 nanometer process with a nominal threshold voltage of 0.3 volts and a doping level of 8 times 10 to the negative 17 centimeters, 1 over centimeters cubed, with a body tied to ground. If the source is at 0.6 volts instead of 0, find the new threshold voltage. So we have this instance where for some reason instead of voltage, the ground being at 0, for some reason is increased to 0.6 volts. So you want to see how much this impacts our threshold voltage. First, we're going to calculate the body effect. The body effect, we're going to substitute charge, 1.6 times 10 to the negative 19 coulombs, EO times KSI, so we have the permittivity of free space times the coefficient for silicon. And we know that our doping level, Na, is 8 times 10 to the negative 17, so we have substituted it here. This is the same thing. I've just, for COX, we have permittivity of the oxide divided by thickness of the oxide. So we have the difference between the gate and the body. So now we are calculating this out. So this is where you use the different values. So here you'd use 11.7, here you use 3.9, because we're specifically talking about the difference between the body and the silicon glass that's keeping it between the gate and the body. So again, 10.5 times 10 to the negative 8, that's the given value for the thickness of the oxide here. And then substituting these values, we get 0.16. Next, to find the surface potential, we multiply 2 times the thermal voltage times the natural log of our doping concentration times the intrinsic carrier concentration. This gives us 0.026 volts times the natural log of 8 times 10 to the 17 over 1.45 times 10 to the 10. And that comes out to 0.93 volts. Finally, we substitute our values. We have our initial threshold voltage of 0.3 plus 0.16 times 0.93, which we calculated here, plus 0.6. And we calculated 0.6 by finding our initial source voltage, and we subtract 0 from that since the body is tied to ground. We subtract 0.93 square root again. When we do this, it all comes out to 0.34. Now, I made a little note here. Body effect, it becomes a very common interview question. That's partially because of forward and reverse body biasing. These are common issues if you want to work on performance versus power consumption. Since we've already learned in dynamic power consumption, CL times VDD squared times the frequency, that power consumption is directly related to the frequency. So what we have to realize is that there's using these body effects and using positive and negative body biasing, we can actually impact the power consumption beyond just what's done in frequency. So knowing this is actually important. It's kind of a confusing concept at first, particularly how to use these. So this is, as you notice in the equation again, notice how it's ESI divided by COX. So it's not the same thing here. So you would not want to use here, you want to use 11.7. You specifically need to use 3.9. So for source to body voltage, particularly if it's small, we're going to worry about a slightly different version of this coefficient, where we have our body bias coefficient, and we're it's divided by 2 times the square root, and now we have our thermal voltage and our natural log, and then we multiply that by 2 COX and when we solve it out. Next, we're going to worry about leakage. So now we've been worrying about how things get pinched off. We're doing a lot with saturation and how we're getting collisions to take place. And we're doing about this body effect and how that affects creating a diversion region around the drain and body. So now we're going to talk about what happens when transistors are off. When the transistors are off, we want them to have no current, ideally. However, they do leak small amounts of current. Leakage mechanisms include subthreshold conduction between the source and the drain. So below this gate level threshold voltage, you're still getting some sort of conduction. You get carrier movement. Junction leakage from the source to the body. So we define these 3 types of sources. So subthreshold voltage occurs because transistors can't abruptly turn on and off. And the dominant source in contemporary transistors, so this means in modern 22 nanometers, where we have to worry a lot about subthreshold conduction, and we realize that because we're decreasing the length between the source and the drain, and as a result, you're actually increasing the electric field and you're increasing conduction. So even when you're below that threshold voltage, you're not necessarily completely turning off the circuit. Gate leakage involves tunneling through ultra-thin gate dielectrics. So we talked about here the gate leakage from the gate to the body. So now you have some sort of tunneling. And then junction leakage is the reverse biased PN junction diode current from the source to the body and the drain to the body. So that's where you have subthreshold current going from here, source to the body, drain to the body. So this I junction is this junction leakage current. And so again, we have this chart up here where we're talking about subthreshold region. We have subthreshold current, and we are worrying about this current fits on a straight line on a semi-log plot, and this is calculated. We have our initial drain source voltage times e to the, this is the whole equation here, gate source voltage minus the initial threshold voltage times the Dibble coefficient times VDS minus KY, which we calculated here, K of gamma, times source base voltage divided by NVT. And then that's all multiplied by 1 minus e to the negative VDS over VT. So grad students, I've kind of given an example here. As well, undergrads are welcome to do this for extra credit. We have the physical explanation of tunneling. It's a 7-minute video, and then you have to write 200 words or something on it. It's not terribly difficult. It gives you just a basic understanding of how quantum mechanics and quantum tunneling actually works. And so if those of you who are actually interested in how this is actually working, you can actually use this to understand it. It's actually meant for high school science and physics, so it's not that terribly difficult to understand. For junction leakage, the PN junctions between diffusion and substrate form diodes, as we've mentioned before. So the PN junction have some leakage of ordinary diode leakage, and we're going to deal with these two concepts here called band-to-band tunneling and gate-induced drain leakage. So if you've seen this chart that I've included a couple times, we have drain-induced barrier loading, and we have gate-induced drain leakage. Band-to-band tunneling is defined here as something that is an instance where it occurs across the junction between the source or the drain and the body when the junction is reverse biased. So it's coming from the source or the drain, so it's band-to-band tunneling. And it's a function of the reverse bias of the doping levels. So tunneling is tunneling across heavily doped PN junctions, especially when the sidewall between the drain and the channel, and we call this halo doping, is used to increase the threshold voltage to account for this. Additionally, gain-induced drain leakage occurs at the overlap between the gate and the drain. It's most pronounced when the drain's at supply voltage and the gate is at a negative voltage. So we now have an instance of our transistor where we have a negative gate voltage, so it's below 0, and the drain is at supply voltage. So now you've actually created an instance where you have 1 and then -1. So you've created quite the potential here between the gate and the drain, and that's where your gate-induced drain leakage occurs. So then you're creating significant difference there. The voltage, which causes an inversion region, well, none that doesn't cause an inversion. Well, I'm going way too far. Doesn't cause an inversion region, but it does allow current to travel. Are we there yet? Wow, I went way too far. Okay. Okay, so I want to talk really briefly about temperature dependence. So we've worried a lot about voltages. So we've worried about length and width and process sizing, but temperature also has an impact. Mobility is reduced when you have the temperature, and the T is the absolute temperature. We have a mobility, so you have room temperature relationship between this and the actual temperature, and Ku is a fitting parameter, which is approximately 1.5. Next, we consider how the threshold voltage is reduced. The magnitude of the threshold voltage decreases nearly linearly with temperature and may be approximated using this equation, where we have the threshold voltage of the function given the current temperature is equal to the threshold voltage for the function at room temperature minus kVt, so it's another fitting parameter, which is approximately 1 to 2 millivolts per Kelvin of the current temperature minus the room temperature. At high gate source voltage, the current has a negative temperature coefficient, meaning that it decreases with temperature. At low gate source voltage, the current has a positive temperature coefficient, and therefore the off current increases with temperature as well, which is one of the reasons why we have very difficult time putting circuits on planets that have very, very high temperatures. For example, if you notice when we send probes to Venus, we end up having problems because we can't get the circuits to work for a long time because the effective conduction of a CMOS transistor really fails after approximately 300 degrees centigrade. This is research that NASA is working on. They are actually using, they're trying to use JFETs for these kind of environments. So they're kind of going back to the old school, what they were dealing with at the exact same time as CMOS transistors. Also, I want to very briefly cover, so you have your normal, as temperature increases, you're going to have increasing gate source voltage. And once you hit, this is compared to the square root of drain source voltage. And then once you hit a certain point, you've got decreasing temperatures versus increasing temperatures. And so once this is transistor off, it's transistor on. So I on will decrease with temperature, and I off will increase with temperature. So now we've talked about layouts, and we're going to talk about electric VLSI designer. And so the effective width and the effective length are equal to the length and width that you're drawn plus your XL and XW by actual gate dimensions here. So these are how the actual gate dimensions are affected by synthesis. And the source and drain should diffuse laterally under the gate, LD and WD. So we have lateral diffusion, and then we have the difference between what was drawn and what was actually made. So usually we want to minimize these as much as possible. Okay, so I want to go over 2.6 here. I have a set of 6 questions, and we're going to go kind of walk through the proof on how to do each of these. And so let's say for linear mode, consider the following. If the width of the transistor increases, the current will increase, decrease, or not change. This is a multiple choice question. We go to our equation sheet. We see that drain source current is impacted by width linearly. So as W increases, IDS will increase. So same thing. If the length of the transistor increases, the current will increase, decrease, or not change. So L negative. So as this increases, that means this quantity will decrease. Therefore, IDS will decrease. If the supply voltage of a chip increases, the maximum transistor current will increase, decrease, or not change. So we're at supply voltage. We know VDD is going to increase. So therefore, VDS is going to increase. VDS will increase. Therefore, IDS is going to increase as well. Number 4, if the width of the transistor increases, its gate capacitance will increase, decrease, or not change. So now we know the width of the transistor is related to the gate capacitance by the oxide capacitance per unit area times width times length. So as W increases, so will gate capacitance. Number 5 follows if the length of the transistor increases, its gate capacitance will increase, decrease, or not change. Again, we use L. L increases, so does CG. 6. If the supply voltage of the chip increases, the gate capacitance of each transistor will increase, decrease, or not change. So we've increased supply voltage. As VDD increases, the gate capacitance will not change since CG is not dependent on the supply voltage, nor does the permittivity of the SiO2. So the permittivity of the SiO2 the permittivity of the oxide, the permittivity of free space, the thickness of the oxide, and the width and the length of the transistor are not affected by the supply voltage, so they will not change. Now we're going to start talking about how we can analyze these circuits. And eventually, later in the course, we're going to learn about SPICE, which is simulated programming for integrated circuits extended, if I remember correctly. I think that's right. Now, digital circuits are merely analog circuits used over a specific portion of their range. So we're going to use the high range and low range, high input, high output, low output, to measure where our values of 0 and 1 are. So we're going to consider the CMOS inverter and what happens in instances where the supply voltage and the gate of VSS, where it's grounded, what happens if they aren't logic 1 and logic 0. So recall we had these definitions earlier in the section. Cutoff, drain source voltage is equal to 0, and gate source voltage is less than VT. And then linear, VGS is greater than VT, and the drain source voltage will increase with a drain source current increases with drain source voltage, and saturation voltage to the gate source is greater than the threshold voltage, and VDS is greater than the gate source voltage minus VT, and IDS is independent of VDS. So now that we've demonstrated we know what the threshold voltage is and we have supply voltage, NMOS transistors pull no higher than VDD minus VTN. We call this a degraded 1, meaning the 1 is on the gate. And we approach degraded values slowly. This results in a low drain source voltage. PMOS transistors pull no more than VTP, and we need transmission gates are needed to pass both 0 and 1. And remember, we have the dual rail pass transistor logic for transmission gates. And so applying these equations in order to figure out how the threshold voltage and the input voltage actually impacts the NMOS and PMOS transistor operation, we are going to talk about, first we cut off, so we had our original gate source voltage N is less than VTN. Therefore, Vin, which we relate to VDSN, because we recall we have our transistor up here, right? So if our NMOS gate source is equal to Vn, because we assume it's 0. So therefore, Vn is going to be less than the threshold voltage. VGS is greater than VTN, therefore Vn is going to be greater than our threshold voltage for the NMOS. Drain source voltage, I'm going to scroll up here so that way as you're writing this down you can refer to the inverter simultaneously, is less than gate source voltage minus threshold voltage. And Vout is less than Vin minus VTN. So here we had our threshold voltage that needs to be applied to Vn. So Vn minus threshold voltage is going to be greater than Vout. And for the saturation mode, again, the gate source voltage is going to be greater than the threshold voltage for the NMOS. Therefore, Vn is going to be greater than the threshold voltage. VDSN is going to be less than the gate source voltage for the NMOS transistor minus the threshold voltage of the transistor. Therefore, Vout is greater than Vin minus VTN. So you're going to notice that we kind of flip all these around for PMOS, and that's precisely because it's the opposite charge. So doing these derivatives again, you're welcome when you write this down to write this one, this one, this one, and this one, and this one, because those are the non-derived. So using the same deriving process and flipping all of the greater than or less than signs, so we get for cutoff PMOS, Vn is going to be greater than VDD plus threshold voltage for the PMOS. Vn for linear is going to be less than VDD plus VTP. and V out is going to be greater than V in minus VTP. And saturation mode, V in is going to be less than VDD plus the threshold voltage, and V out is going to be less than V in minus VTP. So using this, we now can see another example of why we have to double the width of the PMOS transistors, because of the fact that our threshold voltages and the beta and the width of the length impact capacitance, and because of the fact that whole electron mobility is twice as fast as hole mobility, by doubling the width of the PMOS transistor, we can get these IDSN and IDSP to be the same, except they're obviously inverted sign. And when we're talking about IDSN and IDSP, you see that they're actually in different directions. We have positive and negative current. So when we compare IDSN and the absolute value of IDSP, we get this in the ideal situation. So we've gone 50 minutes, right? Is that how long we've gone? Oh, we've only gone 40 minutes. Okay, I can do this then. All right, so the next thing we want to talk about is the transistor operating region. So the important thing about the transistor operating region is now we know where linear, cutoff, and saturation modes are, and we want to figure out how to relate V out and V in. So the modes we want to be in are A and E. So A is when our input value is 0, we want our output value to be 1, right? Here in E, we want our input to be 1 and output to be 0. You see, in A, we have our P device in linear, and E, we have our N device in linear. And then from there, we have a combination of saturation from the PMOS and NMOS transistors that cause degraded performance, as you can see by this chart. So here in region A, from 0 to Vn to threshold voltage of the NMOS transistor, the P device is in linear and the N device is in cutoff. So the supply voltage, the output voltage is going to be equal to the supply voltage. When we cross into region B, what ends up happening is the NMOS device goes from saturation to from cutoff to saturation, and this is because we've exceeded the threshold voltage of the NMOS transistor, but we haven't gotten to VDD over 2 yet. So this is threshold voltage N less than or equal to Vn less than VDD over 2. So in this case, our V out is going to be greater than VDD over 2, but as you can see, we start decreasing. And then what happens is we get a very sharp decrease when we hit the half of supply voltage, like this. And the reason why is because both the PMOS and the NMOS device are saturated. So in region D is what happens when we have supply voltage VDD over 2 is less than Vn is less than or equal to supply voltage minus the absolute value of the PMOS threshold voltage. We have now put the PMOS device in saturation, and our NMOS device is linear for region D, and so our output is going to be less than or equal to VDD over 2, as you can see. And then for section E, Vn is greater than VDD minus VTP, so now it's exceeded the threshold of the PMOS device, so it's gone to cutoff, and the NMOS device has gone into linear. So the TGO, you should be able to do the table as well as this diagram. So I included this diagram here really quickly. The beta ratio, if we double the width of the PMOS transistor, we're able to get the beta ratio to be 1. And this allows us to not have a skewed gate. So when it's 1, it just has our regions as we expect. If you increase or decrease the beta ratio, you're suddenly increasing the amount of time you're in region A. So if you increase the beta ratio, you're increasing the amount of time you can hit a 1, but decreasing the amount of range you get a 0. Likewise, if you have the beta ratio is 1.1, where beta n is 10 times a beta of holes, then you have a lot of time where you're in region E and only very little range where it can be A. So one of the major benefits of doubling the width of the PMOS transistors is hitting this exact operation where it's not skewed. So this curve benefits from having a double PMOS NMOS. So this is where I'm gonna finish this particular lecture, because I want to have time for you to go over the last couple of things. We're not going to go over any of this example here. We're not going to go over noise margin. We'll start noise margins for next lecture. So the homework, which I'm going to write here, is going to be TGO 2.20, and it's going to go through 2.27. And example questions 2.3, and that's going to go all the way through 2.7 here. So I'll post both of these separately on Blackboard, so in order for you to actually do the problem. So here we have an interesting case. We've talked about how PMOS transistors and NMOS are in pull-up and NMOS transistors are in pull-down. Now we have engineers come in. We have a proposed design of a non-inverting buffering circuit. So we have an instance where, say, in theory, you have a 0 on the input. We know that PMOS transistors turn on when you have 0 here. So what they're suggesting is 0 on the input goes to 0 on the output. If you have a 1, NMOS conducts 1 on the output. So this is what the engineer has proposed. So we've assumed that the beta ratios are the same and that the threshold voltage for Vn is equivalent to the absolute value of the threshold voltage of the PMOS transistor. Now, the benefit of this theoretical circuit would be the delay. But what happens when the circuit actually operates in each region of operation? So again, we define VGSN as VDN minus VDD from our TGO. We know that VDSN is VDD minus Vout. For the PMOS, the gate source is equal to Vin, and VDSP is equal to Vout. And the reason why we're able to do that is because for PMOS, Vn is gate source, VDSP is equal to Vout, because here's Vout, drain, source, so that should be 0. So then for the NMOS, gate source is VDD minus Vn, but we've inverted that. VDSN is VDE minus Vout. So ideally, this is what would happen if what the engineer was proposing was correct. We would just invert everything for the PMOS and NMOS device. That in region A, the NMOS device would be in linear, so you have 0, and then you hit saturation for PMOS, and here you have your saturated regions, and then here the PMOS would be linear. But here's the problem, and this is the point of this question and why it's important for you to work through this, is to see what would actually happen in each region if this was actually proposed. So in region A, you're saying that we want cutoff for PMOS and linear for NMOS. We've said that the Vn is greater than VTP, but we know about PMOS transistors, since Vn is 0 in the desired range of operation, that's not possible. So we have proven that Vn has to be greater than VTP here. We also know that for linear, for NMOS, we need the gate source voltage of the NMOS transistor to be greater than the threshold voltage. Therefore, Vn will be greater than Vtn minus VDD. But since Vn is 0, this is also not possible. If you flip it around, that's where we get our actual operation. You flip those, that works just fine. However, since they're trying to make NMOS a pull up and PMOS a pull down, it fails in section A. In section B, same thing, saturated for PMOS, you have gate source of PMOS transistors. We want it to be less than threshold voltage. Therefore, VN needs to be less than VTP. However, since VTP is greater than VDD over 2 for PMOS, it's not possible. We don't want that. For linear for NMOS, say that VDN is going to be greater than VTN plus VDD, but since we want VN less than VDD over 2 for NMOS, and that's not a case, we can't have that, therefore it's not possible. So these cases are what's actually happening, and this is the case that we desire. So saturation, both VDD and for both PMOS and NMOS, they still work the same as before. For D, for linear for PMOS, we desire a gate source of P is less than threshold voltage of P. Therefore, VN should be less than threshold voltage of P. However, since VDD over 2 is TP in section D, which is what we're saying here, this does not meet what we want to happen. Therefore, it's simply not possible. Again, for NMOS, we would want it to be saturated if the engineer's proposal was correct. But to get saturation, we need gate source of N to be greater than the threshold voltage. Therefore, we would want the input voltage to be greater than VTN plus VDD. But that's not possible. It's the NMOS we had plus supply threshold voltage. And finally, we want linear PMOS. The gate source voltage for PMOS would have to be less than the threshold voltage. Therefore, VN would have to be less than the threshold voltage. However, in E, we want VN to be equal to VDD to be equal to 1. Therefore, that's just not happening. Again, for cutoff for NMOS, VGSP this must be greater than the threshold voltage for the NMOS. I don't have P there. It should be N. VN should be greater than VTN plus supply voltage, and that's not possible. So the benefit of working through this problem, this is a very important problem, is for you to understand physically, is a proof why we use PMOS as pull up and NMOS as pull down. So here we have demonstrated that it just simply won't work. Okay, so this lecture has been 52 minutes, allocating an additional 20 minutes or so for questions and timing. That's good enough for today. I'll give you an opportunity. I'm sure that I'll have a lot of questions on Tuesday in lecture about this. So you have the opportunity to ask about the things that we covered. I will be responding to emails, so feel free to send me emails. Additionally, I will post directions on how for you to sign up for SemiWiki. You're going to pick a partner, and you're going to eventually be blogging about some sort of contemporary issue, and then you're going to be interacting with industry people to actually learn about that more. So, all right, well, have a good weekend.